Pre-calculus is looking at polynomial functions, power functions, and rational functions. As we look at the polynomial functions in Chapter 2, we are going to start with a degree 1, that's a linear function, and work our way up. So Section 2.1 looks at the linear and quadratic functions. As you move on to 2.2 and 2.3, you're going to look at cubic functions and quartic functions, and then distinguishing between those higher degree polynomials. So to start in Section 2.1, most of this should seem review from what you have talked about in Algebra 2 already, but we're going to talk about first what is a polynomial function. Here they are giving you the general format of a polynomial, a sub n, x raised to the n, plus a n minus 1, x raised to the n minus 1, and so on all the way, working ourselves down, a with the subscript of 2 here, x squared, a1 times x, that would be to the first, and then finally a naught or a sub 0 at the end where you have your constant term. Now, an example of that would be something like maybe 5x to the 6th minus 8x to the 5th plus 11x to the 4th plus 3x cubed minus 9x squared plus x plus 7. You wouldn't necessarily need to have every single degree listed in this polynomial, but I just wanted to show you that as you're working your way down, you see that this is x with the n as your exponent, n minus 1 being 1 less, so then you see 6, you see 5. Work your way down for the functions. You've got your leading coefficient here is the a sub n. We see that in our definition. The leading coefficient is the a sub n. And the degree of the polynomial that we wrote is the n, meaning the largest exponent that you see. So in some of our examples here, they're going to ask us what's the degree of the polynomial. You're looking for that largest exponent, and the leading coefficient is the coefficient in front of that term. One thing that's very important for us to notice about a polynomial is that n, that largest exponent, is a non-negative integer. In other words, you need a positive number for your exponents in a polynomial function, and integer meaning we're not going to be having any fractions as our exponents there as well. Looking at the names of those polynomial functions, we know that we might have the 0 function, f of x equals 0. We might have a constant, linear function, ax plus b is that general format, and then quadratic. Now, when we're talking about those functions, we can list the degree of each of those. If you're just talking about y equals 0, the degree is undefined. There is no degree there. A constant would be degree 0. A linear function would be degree 1, and quadratic is degree 2. Again, keep in mind the degree is the largest exponent that you're seeing. So in the quadratic here, the largest degree is 2, or the largest exponent is 2, making it degree 2. The largest exponent in a linear function is 1. And then a constant, degree 0, because there are no x's there. You could write that as x raised to the 0. Remember, anything to the 0 power is equal to 1, so that just leaves you with your constant anyway. Another quick reminder for you is that we can also name our polynomials based on the number of terms. So if our polynomial just has one term, that would make it a monomial, something like 3x squared, that's a monomial. Binomial could be something like x plus 7, that's a good binomial, but it doesn't have to be just a linear binomial. So this was a binomial that's a degree 1. You could also have a binomial of something like 3x squared plus 8x. That would be another good binomial. Now it's a quadratic binomial. Trinomial has 3 terms. Maybe we have x squared plus 8x plus 2. And then a polynomial is usually the name that we would give if we have 4 or more terms. However, technically, all the other 3 names that we gave you are also polynomial functions. So a monomial is a polynomial, a binomial is a polynomial, a trinomial is a polynomial, but we will want you to give the most specific name possible as you are listing them in our next examples. All right, so in these examples, you can take a minute to pause the video to see if you can determine the leading coefficient, degree, and the name based on the number of terms for the examples that are given here. After you have taken a look at A through E, you can unpause and go through the answers here. In letter A, the leading coefficient is going to be 4, as we see the 4 out front here, the degree is the largest exponent you see. That's going to be a 3. Name based on the number of terms, that's going to be a trinomial for us. In letter B, looks like our leading coefficient is 11. The degree is 2. Name based on the number of terms is a binomial. Letter C, leading coefficient is 2, degree is 1, name based on the number of terms, again, is a binomial. Letter D, a constant there. That constant leading coefficient we're going to say is 4, degree is 0 for the constant, and it is just one term, making that a monomial. Letter E, the most tricky one in the bunch here, that leading coefficient is not the 5 because that's not where your largest exponent is. So when we check this one out, we see the negative 8x to the 11th. That's going to make our leading coefficient be negative 8. Our degree is going to be 11, and because it has more than 3 terms, we're just going to call this one a regular old polynomial. Now, letter E was the exception to all the rest of them because it was not written in what we would call standard form. What's standard form? Standard form means that the terms of our polynomial are listed in order from greatest to least degree. So, for example, in that letter E that you just looked at, if I was going to write that in standard form, I would put that negative 8x to the 11th first. Then we would look at the 5x cubed, then the 2x, and finally the 1. The signs stay with the term, and we write it in order from greatest degree or largest exponent to the smallest exponent that we see there. Now, going back to our definition of a polynomial, it said that n was supposed to be a non-negative integer. So some examples of functions that are not polynomials, check out letter A here, 6x to the negative 4th plus 5x. Negative exponent is not going to be a polynomial. Letter B, we see the square root. Let's remind ourselves that if we were going to write the square root of x, that is equivalent to x to the 1/2, and so that would not be an integer for your exponent, so that is also not a polynomial function. And finally, 1 over x. Now, I see that this is x to the first in that denominator, which is positive and is an integer. However, 1 over x, that puts that x in the denominator, which is not part of the definition of a polynomial, so that is equivalent to x to the negative first. Therefore, that's a negative exponent, and this does not count as a polynomial either. So in talking about linear equations in this section, we know our basic format, y equals mx plus b. Sometimes you see ax plus b, that's our general format for a linear equation. You're also certainly familiar with the fact that m is your slope. One thing that we're going to be asking you about in this section is using some other terminology that means the same as slope. So we see m in our general linear equations. We know that m represents the slope. Let's not forget that the slope is our rise over our run. Let's not forget that the slope is also our rate of change. Sometimes you're going to hear that as your average rate of change. So our average rate of change is the same as the slope. Another one that's pretty common to us, y2 minus y1 divided by x2 minus x1. In this section, the only terminology that is sometimes new to us is writing the change in y over the change in x in what we would call function notation. So you certainly have seen this one with the y2 minus y1 over the x2 minus x1. But now, instead of calling our coordinates x and y, if we write them in function notation, another option would be to write a as my x value and f of a as the coordinating y value. Likewise, b as the x value and f of b as the y value. So if those were my two coordinates, I would write that in our slope form as y2 minus y1, that's f of b minus f of a, and then b minus a. So we just want you to be familiar with that format as well. Another thing that we know about linear functions, if we have a linear function, the rate of change is always constant. The rate of change, that's that slope. And in a linear equation, the slope stays the same. If I have y equals 3x plus 5, the slope of that line is 3 everywhere on that line. If x is 1, the slope is still 3. At x equals 5, the slope is still 3. At x equals 10, the slope is 3 all the time on this entire graph. So a couple of examples for us. Example number 1, write an equation for the linear function f satisfying the given conditions, and then we want to do a graph of y equals f of x. So when they're giving us the points that we're going to use to write this function, they're giving us f of 1 equals 2 and f of 5 equals 7. I would ask you to take a second, pause if you need to write out those coordinates. If I was doing this live in class with you and I asked people to write out the coordinates, usually every year, probably about 40% of the people, maybe a little bit more than that, maybe would write our coordinates incorrectly. So take a second. What coordinates would this function notation represent? All right, let's see if you got the right answer. If it says f of 1 equals 2, that would be the coordinate 1, 2. If it says f of 5 equals 7, that's going to be the coordinate 5, 7. So again, make sure that you're writing that in the correct order. It's pretty common for people to flip-flop that and tell me that this is the point 2, 1 and this is the point 7, 5. We don't want to be making that mistake. One easy way to remember that is that this is f of x, so the x value goes inside the parentheses, and f of x is equal to y, so inside the parentheses is the x, and it's equal to the y value. That's the 2 value that you see there. All right, so now that we know what our coordinates are, let's go ahead and calculate the slope. Again, the slope is your change in y over your change in x. So if we subtract the y values, I'm going to take 7 minus 2, subtract those x values. That's going to give me 5 minus 1. Looks like my slope is going to turn out to be 5/4. Once I have that slope figured out, then we can go ahead and put this into our linear equation. Y equals mx plus b is what we know as our standard format for that linear equation. We just figured out that our slope was 5/4, so I'm going to substitute that in for m. The part of this equation that I also know is I do know an x and a y coordinate. So I'm going to pick one of my points in blue here to substitute in for the x and the y values. If I have a calculator, no point is really any harder than the other, so I'm going to pick the coordinate 1, 2, but I could also pick the coordinate 5, 7. If I don't have a calculator, I usually like to pick the one that's going to be easier to do the mental math on, but with a calculator, you can pick either point that you like. Of course, looks like I get 2 equals 5/4 plus b. Solve for b means I'm going to subtract that 5/4. And 2 minus 5/4, that's going to give me 3/4 altogether for my value of b. That means if I'm going to write my final answer, remember they asked us to write an equation for that linear function, y equals 5/4 x, 5/4 was my slope, plus 3/4, which is my b value, as my final linear equation. Now it also does ask us to sketch a graph of that, so I would let you put that into your graphing calculator to sketch the graph and ensure that it does in fact go through the points 1, 2, and 5, 7. Next example for us on this sheet is looking at Camelot Apartments bought a $50,000 building, and for tax purposes they are depreciating that at $2,000 per year over a 25-year period using straight line depreciation. What is the rate of change of the value of the building is what they're asking us for in letter A. It says that they're depreciating it $2,000 per year over that 25-year period. So the rate per year is $2,000 and it's going down. So I'm going to say that that rate is negative $2,000. Letter B asks us to write an equation for the value v of t of the building as a linear function of the time t since the building was placed in service. So instead of a y equals, they want us to use a v of t. We figured out that the slope was negative 2,000. So we're going to have negative 2,000 times t. And the b value, remember b is our starting point. So what's the starting point of the value of this function? Looks like the $50,000 here. And that's our v of t equation. Now we're going to use that v of t equation to evaluate in letter C and also in letter D. Letter C asks us to evaluate v of 0. V of 0, of course, means that I'm putting 0 in for that t. And putting 0 in for t is going to leave me with 50,000 as the value that I start with. V of 16, again, t meaning the time. So after 16 years, what's that value? We've got negative 2,000 times 16 plus 50,000. And that should give me 18,000 as the current value after 16 years. And letter D, solve V of t equals 39,000. So we can set that up as a nice equation. It says V of t is the 39,000, so I'm going to put 39,000 as my starting value here for V of t. 39,000 equals negative 2,000 t plus 50,000. What that's basically asking us is, when is the value $39,000? So we're trying to figure out at what time is the value of this building, 39,000. And so we'll solve for t. I'm going to subtract that 50,000 over and divide then by the negative 2,000, and that's going to give me a t of 5.5. So therefore, that's at 5.5 years. And we'll just go ahead and leave that decimal for now. 5.5 years that the value is that 39,000.